Think back to the multiplication rule that helped us calculate the probability of the intersection of two events. The probability of A intersect B is the probability of A given B times the probability of B. As the intersection of A and B is the same as the intersection of B and A, the probability of A intersect B is the probability of B intersect A. That means that the probability of A intersect B is equal to the probability of A given B times the probability of B, and is also the probability of B given A times the probability of A. This means that the probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. Dividing both sides by the probability of B gives us an alternative way to calculate the probability of A given B if we can quantify the probability of B given A. This result is referred to as Bayes' theorem. It's named after the Reverend Thomas Bayes, an 18th century English Presbyterian minister and amateur statistician. His inverse probability problem was published after his death and has become very popular in calculating a particular conditional probability that can't be directly viewed and is estimated from probabilities that can be viewed. So when do we use Bayes' theorem? When the problem begins with a stated probability, the probability of A, and more information is gathered, usually via imperfect testing or forecasting, and we know how often this new information is right or wrong, the probability of B given A. Ultimately, we want to know how the new information changes the probability of the event, the probability of A given B. Let's illustrate this idea with an example. Stephanie is getting married tomorrow at an outdoor ceremony in the desert. In recent years, it has rained only 5 days each year. Unfortunately, the weatherman has predicted rain for tomorrow. When it actually rains, the weatherman correctly forecasts rain 90% of the time. When it doesn't rain, he incorrectly forecasts rain 5% of the time. What we want to know is, what is the probability that it will rain on the day of Stephanie's wedding? Let's first define the events and the probabilities that we know. Define event R as the event that it rains on a particular day. The probability of R is 5 out of 365, as in recent years it has rained 5 days per year on average. Let's define another event, F, which is the event that the weatherman forecasts rain. Note that this is different than it actually raining. This is a forecast of rain. How accurate is the weatherman? Given that it actually rains, the weatherman correctly forecasts rain 90% of the time. That is, the probability of a forecast of rain, given that it does actually rain, is 0.9. Similarly, how good is the weatherman at forecasting rain when it doesn't rain? The probability of a forecast of rain, given that it doesn't actually rain, is 0.05. Here, doesn't rain is the complement of rain, or rain complement. So let's lay out everything we know. We know the probability of rain in general is 5 out of 365. Therefore, we know the probability of no rain, the complement of the probability of R, which is 360 out of 365. We know how good the weatherman is when it rains. That is, the probability of F given R, which is 0.9. Therefore, we can calculate how often he's wrong when it rains, the complement of 0.9, which is 0.1. We also know how often the weatherman makes a mistake when it doesn't actually rain, forecasting rain instead, with probability of F given R complement equal to 0.05. And the complement of this is the probability that he correctly forecasted no rain given that it didn't rain, or the probability of F complement given R complement, which is 1 minus 0.05, or 0.95. This generally falls in line with a Bayes' theorem storyline. We know the probability of an event, the probability of A. We gather some information, in this case a forecast, and we know how often that forecast is right and wrong, with the probability of B given A. And we ultimately want to know the probability of A given B, the probability of the event, given that the forecast told us that the event would occur. Here, the probability of A given B, or in this case, the probability of R given F, the probability that it will rain when we have a forecast of rain, isn't observable. We only know how often it rains in general and how good the weatherman is at forecasting rain and no rain. Let's implement Bayes' theorem to solve this problem. Recall that the general formulation is the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Using the events associated with our problem, the probability of R given F is equal to the probability of F given R times the probability of R divided by the probability of F. We have the probability of F given R, we have the probability of R, but we don't have the probability of F. However, we can find the probability of F using some of our probability rules. Recall that the probability of F can be found as the probability of F given R times the probability of R, plus the probability of F given R complement times the probability of R complement. Remember, R and R complement are mutually exclusive and collectively exhaustive. So this probability rule works out. So we're left with the Bayes Theorem formulation you see on the screen. And we have all the probabilities that make up this calculation. In the numerator, we have 0.9 times 5 divided by 365. In the denominator, we have 0.9 times 5 divided by 365 plus 0.05 times 360 divided by 365. The result is a probability of 0.2. That is, there's a 20% chance that it will actually rain on Stephanie's wedding day, given that the weatherman said it would. Only a 1 out of 5 chance? That's a little low. Why is that? Because the weatherman's forecast is not perfect, and because it really doesn't rain very often in the first place. It's important to ask the right question. In Stephanie's case, the weatherman might say, I rarely forecast rain when it doesn't rain, and I'm good at forecasting rain when it does rain, so your wedding is doomed. But that's not what we're asking. We want to know, given the forecast of rain has occurred, what's the likelihood that it does indeed rain? F given R is very different from R given F. Let's illustrate that difference with a scenario. Say you're interested in a female human, but she's taking longer than usual to respond to your Facebook messages. One reason for that might be that you refer to her as a female human. But let's talk about this some more. Your friend might tell you, she's not into you anymore, brah, because if she doesn't like you, the chances are high that she won't respond as quickly to your Facebook advances. That last part is true. If she indeed doesn't like you, she probably isn't going to respond quickly to you. But you haven't witnessed that. You've only witnessed that it's taking her a while to respond. There could be a lot of reasons for that. She might be studying, or her phone battery might be dead, or she's in a movie theater or something. There could be many reasons why it's taking a while to respond. So, the chances that she doesn't like you if she takes longer to respond are probably much lower than the chances that she takes longer to respond if she doesn't like you. These are two entirely different conditional statements. The first one describes our situation. We witness that it takes longer to respond, and we're drawing the conclusion that she doesn't like us. The second statement is more likely. Given that she doesn't like us, she'll take longer to respond. But we didn't witness the event, she doesn't like you. We only witnessed the event, she takes longer to respond. The point. We need to be careful in interpreting conditional probability statements and make sure we're witnessing what we think we are.